Hi all, this is Mr. Yeager with chemistry, finishing up our unit on solutions by looking at this thing called colligative properties. So this is something specific to solutions. I'm going to start off with that question we see there. Why do we put salt or brine solution on roads before ice storms? You've heard that in the news constantly. I mean, that's something that's regular in the winter. And the reason is, they say it will make sure that the ice doesn't freeze. So why would ice not freeze at 0 degrees Celsius if it's below the freezing point in the air and on the ground? And it's because there's this thing with a colligative property of the solution where we can actually lower the freezing point of the solution itself. So how does this work, and what are other types of colligative properties that we have out there? So a colligative property is a physical property, not a chemical property, but a physical property of the solvent. So again, we're looking at the solvent of the solution. It actually doesn't matter what the solute is per se. Okay, obviously the type of solute will have some effect on it, but we are only changing the physical property of the solvent based on the concentration and the number of solute particles that will get dissolved. And that is that there are 4 properties that are affected by this that we will go over. 2 that we will actually do some calculations with. 2 that I just want to mention about them and why they would happen that way. So it's a physical property of the solvent based on the concentration in molality. So this is why we learn molality. And then the number of solute particles dissolved in the solution itself. So there are 4 colligative properties. Okay. The one from the initial scenario was freezing point depression. So that's the one that we are manipulating of the solvent. All right. So most of the time we're looking at water and we're going to lower the freezing point from 0 to something less than 0 so it won't freeze. The reason this happens is basically the solute particles will disrupt the ability of the solvent to essentially form crystals. Or again, when water wants to come together, I mean, they have to arrange themselves again into a solid, compacted, crystallized form. And if you have these solute particles in between, they can disrupt them, forming those intermolecular bonds more carefully with each other. And it takes a little bit more time for that to happen, or it has to occur at a even lower temperature. You have to even slow those particles down even more in order for it to freeze. So that's why freezing point depression occurs. The opposite happens at the other end of the spectrum, boiling point elevation. All right, this boiling point in the end, I know we didn't really talk about it too much at the beginning of the year, but a boiling point depends on the vapor pressure of the solution. When the vapor pressure of the solution matches that of the air pressure around it, the solution will start, or the solvent will, the liquid will start to boil. All right, and so there's another one you can see at the end there, vapor pressure lowering. So these boiling point elevation and vapor pressure lowering obviously are working hand in hand. What happens is we will lower the vapor pressure of the solution, which means it will take more temperature, more energy in the particles to get them to that higher pressure and therefore boil at a higher above 100 degrees Celsius. Again, if we're talking about water, a higher temperature for it to boil, essentially. Okay, so I'm going to actually skip from I'm going to skip over osmotic pressure and go back over to vapor pressure lowering. What is vapor pressure? Vapor pressure, what happens with any liquid is there's always some of the particles that are escaping from the liquid state. They are evaporating. We talked about that. Evaporation is where particles are changing into a gaseous state below their normal boiling point. And that's just because they might just barely get enough energy where they're able to break those intermolecular bonds and become on their own. But once they kind of come back around and touch the water again, they'll generally basically condense again into the water. And this is a continuous cycle, all right, that goes on and on. It turns out when we have higher concentrations of solute particles in the solution, they're able to hold more of that solvent into the solution itself. Basically, they help create more intermolecular bonds to pull that vapor in more and make it more difficult for those particles to escape, all right, essentially. So that's what we're looking at there with vapor pressure lowering. The last one, just to kind of mention it, is osmotic pressure. This is the pressure basically to move water obviously back and forth across a particular membrane. Clearly, if you have a lot more salt on one side, you're going to create a higher osmotic pressure, because the idea is osmosis wants to balance out the concentrations of two sides of a solution. All right, this is obviously happening in your cells or any sort of membrane situation that we might have here. But it creates this pressure that occurs because what happens is the water might be like, oh my gosh, there's so much salt on this side, it wants to move across the membrane, so it increases the pressure between the two. All right, that's what we're looking at with osmotic pressure. There is a calculation with that where basically it does actually include that mole fraction that we mentioned, but we don't really need to cover that in our particular class this time around. It's something, if you move into a general chemistry, high school chemistry situation, you will start calculating out osmotic pressure as well. Osmotic pressure. Okay, so that's what we're looking at there. So these are our 4 colligative properties. This is all changing the solvent physical properties of freezing point, boiling point, osmotic pressure, and vapor pressure. The thing is, all of them are directly related with the amount of solute. The more solute you have, the more depressed the freezing point is, the more higher the elevation, the more pressure there is, the more osmotic pressure is, the lower the vapor pressure it is. All right. So the name is essentially there. All right. I mean, what should happen to the property is in the name of the colligative property, other than osmotic pressure. Okay. We can technically be like osmotic pressure raising, but we don't call it that. Okay. So that's what we're looking at with these 4 colligative properties. Now, 2 of them, the boiling point elevation and freezing point depression, we're going to look at their formulas. We can actually play around with these. We could do a lab with these. This is, again, the idea where we might be, almost create ice packs and hot packs based on how much we put into it. No, sorry, that's not correct. This is where usually, I'm thinking about a different lab. I usually make slushies with the students where we can go ahead and create these different types of situations by lowering the freezing point of the object. Okay, so we have 2 formulas. You'll see that they're very similar, and I'll do a couple examples to show you how this works. Okay, usually this is delta T. I just couldn't do that in the Google site thing here. But what we have is the freezing point depression formula is delta T, where delta T is the change in the temperature that it's occurring to the freezing point, will equal this I times Kf times lowercase m letters. So what do those all mean? We know what m is. M is our molality. So we're bringing back moles over kilograms of solvent. So this is our one big use of molality, which is why we introduced it back in the concentration part. Okay? So we do need to know the molality of the solution. Okay? Then there's 2 other things. There's Kf. Kf is known as the freezing point depression constant. All right? The freezing point depression constant. So it is something that should be given to you in a problem, or I have to give you everything else and I make you solve for what is the constant. Usually, though, it's given to you. All right? It is in units of degrees Celsius over molality, because the idea is we should cancel out the molality and we're changing the temperature. It's going to tell you how much the temperature will change by based on the molality. But then we have this what's called Van Hof Factor, okay, which is this little I. Let me explain this one. This is basically just a number, a whole number, okay? The Van Hof Factor I is telling you the number of particles, I'm going to put slash ions, in solution. Number of particles slash ions in solution. So this is going to be just a 1, 2, 3, 4, 5, 6, 7 number that I'm multiplying everything by. Okay? But it's something we have to pay attention to. How do I figure out the number of particles of the solute in the solution? Okay? Well, what I look at is I go, do I have an ionic compound or do I have a basically covalent compound? Okay? If it's ionic, ionic means it's made of ions. So if I'm talking about like NaCl, when I put NaCl into solution, it becomes Na plus and Cl minus. So how many particles are there in solution when I dissolve sodium chloride? There are 2. So I would equal 2 for sodium chloride. If I had something like CaF2, calcium fluoride, well, this would create Ca plus 2 plus 2 F minuses. So how many particles would be dissolved if I dissolve calcium fluoride? That would be I equals 3. So that's what I mean by the Van Hof factor. It's the number of ions or particles in solution. All right. Now what about particles? Well, if it's a covalent compound, and usually we just use something like sugar, where it might say C6H12O6. The thing is, sugar is not ionized. We're not going to separate sugar into 6 carbons, 12 hydrogens, and 6 oxygens. Basically, covalent compounds, the Van Hof factor is always just 1. Because those particles, if they do dissolve as polar particles, sugar is actually polar, all right? It will just still be sugar, it just will get surrounded completely by the water particle, okay? So the Van Hof number for covalent compounds is essentially 1, always, all right? It's only ionic that we have to pay attention and go, how many, you basically just count how many atoms are in the compound. 1, 2, 3, 1, 2, 3, okay, for ionic. Covalent, it's equal to 1. Now, a nice thing going over that, boiling point elevation, we basically do the exact same thing. Sorry, I even showed the Van Hof factor down there. The boiling point elevation would be the change in the boiling point equals I times Kb, which is the boiling point elevation constant, times m, the molality, okay? And so exact same process occurs. A lot of times I make students solve for both because if you know one, you know the other one as well. You just have to use the different factor. The only change is Kf and Kb. We then will add that or subtract that from the boiling point or freezing point respectively. Add to the boiling point, subtract from the freezing point that might be given to you. Okay? So, if you need more again about Van Hof factor, all right, there it is. I'll let it sit for a second just so that you can see that. Again, most covalent compounds, the last statement there, they do not dissociate, they do not break up into individual particles or ions, so that's why most covalent compounds, we simply have 1 for the Van Hof factor. Okay? So let's go ahead and check out a couple of examples here. Oops, wrong thing there. Okay? A couple of examples. What we got here? Oh, I need a calculator. Sorry. I can do this. All right. So what is the freezing point of sugar water solution of 0.05 molal sugar water? Okay, basically just repeating myself. Let me go and just mention this. Basically, almost all these examples are the Kb and Kf for water. Okay, so these are for water that I'm going to be using. Okay, the Kb for water is 0.512 degrees Celsius over molality. So the boiling point elevation, you're going to see the boiling point will not change that much generally for most substances. It's a small factor. The freezing point coefficient is 1.86 degrees Celsius per molal. Okay, so it's a little bit larger there. It's actually just usually more difficult for those crystals to reorient themselves to basically completely solidify. Okay, so for this one, I have sugar water. Sugar is covalent, so I equals 1. It's only asking me what the new freezing point will be. So I would do delta T equals 1, the Van Hof factor, times Kf, which is 1.86, times the molal, which is nicely given to me in this problem, 0.05, and that will equal a change in temperature of 0.093 degrees Celsius. Now, what does that mean? Well, what's the freezing point for water? This is not officially my answer. That's how much it's going to change by, okay? What I actually do is my new freezing point for water would be 0. That's my regular freezing point for water, minus 0.093, so it equals negative 0.093 degrees Celsius. Okay. So that's what we're looking at there. So that's as easy an example as you can get, where everything's kind of given to you and I just have to give you the constant with it. But that's how much it would change by. Let me just do the boiling point elevation. Okay. And a lot of times we usually add like F and then B here after the T just to kind of distinguish it. But it would be 1 times 0.512 times 0.05. So this would be 0.512 times 0.05. The boiling point change would be 0.0256, which I would add to 100 degrees Celsius. So my new boiling point would be 100.0256 degrees. So clearly doesn't change too much for the boiling point in this situation. Okay, almost boils the same as water. You'd almost barely be able to tell. Okay, all right, so let's try another one here. I'm going to find another one here. All right, let's do this one so we can practice molality again. Okay, so it says find the freezing point of a solution made of 160 grams again of sugar dissolved in 2,500 grams of water. Okay, so I'm going to be using delta TF, I'm going to write the F there too, equals I times KF times molality. Well, I have again a covalent compound, so my I is 1. My KF for water is 1.86, and all I need is my molality. So I need to change this into moles, and I need to change the 2,500 grams of water into kilograms. So that would be, I'll just show that calculation first because I need to go back and find the molar mass. It would be 2.5 kilograms of water. Okay, for sugar, 12 times 12.01. Again, I'm doing this assuming you understand how to find your molar mass. This is 342.12 is 1 mole. 126 divided by 342.12. I get a mole value of 0.368. I'm going to essentially divide these two, moles over kilograms. And this comes out to essentially 0.147 molal. 0.147 molal. So to multiply that times 1.86 times 1, and my freezing point will change by 0.273 degrees Celsius. And so then it would be 0 minus 0.273 equals negative 0.273 degrees Celsius is my new freezing point. Okay. All right. I want to do one where we actually have a Van Hof factor. You can see, I mean, on some of these other ones, that one's again just usually doing freezing point. I don't know why they're all doing freezing point. I guess I'll show this one just really quick, where it's showing you that the water will freeze at negative 3.26 degrees. So clearly the freezing point depression is negative 3.26 degrees Celsius. Okay, so if I want to solve for this, I would actually just change that as positive 3.26. It's saying a non-volatile compound. I'm going to assume that just means 1. If it says anything like that, it's just 1 for the Van Hof factor. Freezing point depression 1.86, and it wants to know what the molality is. We would just do it this way. So 3.26 divided by 1.86. The molality of this solution is 1.75 molal. Okay, so just rearrange to solve what you need for. All right, let's find a one where we have a different Van Hof factor. I know I have one down here. There we are. Okay. Oops. Shoot, it's going to make that go there. Okay. So this one's being nice though because it's giving us the molality again, but it says what's the expected change in the freezing point of water for an aqueous solution that is 0.015 molal AlCl3. Well, this right here is an ionic compound, which means it'll split up into all of its ions. What that shows is it will form Al3 plus and 3 Cl minuses every single time one of these particles is dissolved. So that gives me a total Van Hof factor of 4. So for this one, it would be the change in temperature would equal 4 is the Van Hof factor times 1.86 times 0.015 molal. So 4 times 1.86 times 0.015. The change in temperature there is 0.11. With our numbers here, we got 2 sig figs, so basically 0.11 degrees Celsius. And then we go 0 minus 0.11 equals negative 0.11 degrees Celsius. And that is your change in temperature. All right. And I know all of these were showing the freezing point depression over and over again. I mean, the exact same thing would occur with the boiling point. If I do that one more time, it would be 4 times 0.512, that's a 5, times 0.015. If I did that, this is a change of 0.031 degrees Celsius, which then I would add to 100, and so it would be 100.031 degrees Celsius new boiling point. Okay? As I just trail off with my voice. So that is essentially it. So again, colligative properties, physical properties that we change of the solution, of the solvent specifically. We got boiling point elevation, freezing point depression, osmotic pressure, and vapor pressure lowering. Most of the names clearly say what's going to happen with it. The Van Hof factor is all depending on whether it's ionic or covalent. Mainly ionic is when we have to pay attention, otherwise it's 1. And we need to use the molality concentration formula instead of molarity. So that's essentially it. Thank you very much and hope you stay well.